Welcome to Ordinary Differential Equations, Lesson 26, Solving Non-Homogeneous Systems of Equations by the Method of Variation of Parameters. Let's review first the homogeneous case, x prime equals a times x. So we're going to consider that equation where A is an n by n matrix of constants. It turns out that in this case, that system of ordinary differential equations will have n linearly independent solutions. Our mission is to find them. The matrix A will have n linearly independent generalized eigenvectors, and we'll define generalized eigenvectors shortly. Each of these generalized eigenvectors can be used to find a solution of x prime equals a times x. So to solve this system of differential equations, x prime equals a times x, matrix A times a vector function x, we'll find the characteristic equation for A. That characteristic equation, remember, is the determinant of A minus lambda times the identity equals 0. This is going to be a polynomial equation in the variable lambda, and it's going to be nth degree. We'll factor it. We'll use that factorization to find a set of n linearly independent generalized eigenvectors of A. Using these generalized eigenvectors, we will be able to find n linearly independent solutions to the system of ordinary differential equation, and by looking at an arbitrary linear combination of those, we will find the general solution of the system of homogeneous ordinary differential equations. Still considering the system of homogeneous equations, suppose the characteristic equation of A, the matrix A, is the following. Lambda minus lambda 1 to the m sub 1 power, lambda minus lambda sub 2 raised to the m sub 2 power, through lambda minus lambda sub k to the m sub k power equals 0. Then we're going to do the following. We'll look at each of these factors separately. So for each I, let's find a set of m sub I linearly independent solutions to this equation, A minus lambda sub I times the identity matrix, this stuff raised to the m sub I power, applied to the vector v, or multiply this matrix times the vector column vector v, equals a 0 vector. The solutions to this equation are the solutions v to this equation are called generalized eigenvectors of A associated with that eigenvalue lambda sub I. So we're going to find generalized eigenvectors corresponding to lambda sub 1 in this factor. We'll find generalized eigenvectors corresponding to lambda sub 2 all the way through generalized eigenvectors corresponding to lambda sub k. So let's suppose the characteristic equation has a factor of the form lambda minus lambda sub I raised to the m sub I power in its full collected factorization. If m sub I equals 1, then this is just going to be lambda minus lambda sub I to the first power. In that case, v, that generalized eigenvector we're looking for, will be an eigenvector corresponding to that eigenvalue lambda sub I. And then one solution to the system of homogeneous equations is going to be the vector valued function f of t equals e to the lambda sub I t times an eigenvector corresponding to lambda sub I, corresponding to the eigenvalue lambda sub I. So we just get this exponential function times an eigenvector in that case. Now, if we have a power here that is greater than 1, so m sub I equaling 2 or 3 or more, in that case, what do we do? If m sub I is greater than 1 and v is a generalized eigenvector for lambda sub I, then one solution to the system of homogeneous differential equations, x prime equals a times x up here, is the following function. It's a vector valued function. F of t equals e to the lambda sub I t times that generalized eigenvector v. So far it looks very similar to what we have up here, but now we have lots of other terms. Plus te to the lambda sub I t times the matrix A minus lambda sub I times the identity times that generalized eigenvector, plus t squared over 2 times this exponential times this matrix squared times v, plus all the way through t to the m sub I minus 1 over m sub I minus 1 quantity factorial times that exponential times this matrix raised to the m sub I minus 1 power times that generalized eigenvector. Now, in many cases, once one of these terms turns out to be 0 perhaps, for instance, suppose that this one is 0 here, then a raised to this power times v is the 0 vector, and so later terms are going to have higher powers of this same matrix times v. Those will also be the 0 vector. So in many cases we have one or more 0 terms here. So don't be surprised when you see that in a calculation. So up here, when we're talking about this stuff, there are m sub I linearly independent generalized eigenvectors corresponding to that eigenvalue lambda sub I, and there are m sub I linearly independent functions, capital F, looking like this, corresponding to that eigenvalue lambda sub I. So for one particular eigenvalue, if we have an exponent here that's greater than 1, we're going to get more than one function f out of that. Still considering x prime equals a times x with this characteristic equation. This characteristic equation has degree n, so the sum of these exponents here has to be n. The sum of the m sub i's has to equal n. If we find a set of m sub I linearly independent generalized eigenvectors corresponding to lambda sub I, then we get m sub I linearly independent vector function solutions from these generalized eigenvectors. And if we do this for each of these eigenvalues that we see in this equation, we'll get n linearly independent solutions, which we'll call f sub 1 of t, f sub 2 of t, through f sub n of t. Solutions to x prime equals a times x. Actually, we'll find linearly independent solutions. And so the general solution then is just an arbitrary linear combination of these n linearly independent solutions to this system of n equations in n unknown functions. So now we consider variation of parameters, the method for solving a system of non-homogeneous differential equations, such as this one. The derivative of y with respect to t equals a times y plus g of t. So remember that y is a column vector, and a here is an n by n matrix. G of t is also a column vector. So if we write this out explicitly with those columns, the derivative of y with respect to t is y1 of t, y2 of t through y sub n of t in this column equals the n by n matrix A times y sub 1, y sub 2 through y sub n in this column, plus the column vector g sub 1, g sub 2 through g sub n. And remember here that A is an n by n matrix of constants, real numbers or complex numbers. In our case, real numbers. So what is the method? First step, we solve the corresponding homogeneous system of ordinary differential equations. The derivative of y with respect to t equals a times y. And let's suppose the solution is y of t equals an arbitrary constant c1 times f1 of t plus c2 times f sub 2 of t plus c sub n times f sub n of t. The crucial first step in variation of parameters, which will be our step 2, is to replace these arbitrary constants c1, c2 through cn up here with unknown scalar functions, u1, u2 through u sub n. And so y sub t will be the sum over all k, u sub k of t times f sub k of t. So we're looking at this as a possible solution to this non-homogeneous equation that we have up here. And our mission is to find out what these u sub k's are. So we'll substitute this proposed solution into that differential equation and see what happens. Solve for a system of functions, a set of functions, u sub k of t, that will satisfy this differential equation. So in variation of parameters, let's look at what we can do in step 2. Suppose that this differential equation, this system of homogeneous differential equations, has the general solution, the sum of the c sub k, f sub k of t's, where the c sub k's in this case are arbitrary constants. So then, since the derivative of y with respect to t equals a times y, if this satisfies this differential equation, then plugging this into both sides of this equation gives us the sum of c sub k f prime f sub k prime of t, the derivative of f sub k evaluated at t, equals a times the sum of the constant c sub k f sub k of t. So now what we'll do is let u sub k of t be any set of scalar functions of t. They're not really any. We're going to put requirements that the u's have to satisfy. And we'll pick a number t naught, but for now, no matter what u sub k's we pick, and no matter what number t naught we pick, as long as all these u's are defined at t naught, then for each k, let's let c sub k equal u sub k of t naught. Then each c sub k is just a number, a scalar. So if we look at the sum of u sub k of t naught, f sub k prime of t, since this is equal to c sub k, we can write this as the sum of c sub k f sub k prime of t. And by the fact that we know that this satisfies this equation, this right here has to be true. So this thing has to equal a times this sum. But for this sum, remember the c sub k's are u sub k of t naught. So what we have here is the sum of u sub k of t naught f prime, f sub k prime of t is equal to a times the sum u sub k of t naught f sub k of t. And this holds for all values of t naught where these u functions are defined. So what we can then say is, well, let's just use a t here instead of a t naught, since this is true for any value of t in the domain of these u sub k functions. So what we end up with is the sum of u sub k of t, f sub k prime of t, the derivative of f sub k evaluated at t, is equal to a times the sum of u sub k of t, f sub k of t. This holds whenever we have these f's coming from this formula up here for the general solution to this differential equation. So we have successfully found a relationship between this equation with, I guess you can say, arbitrary constants c sub k, and this equation holding for arbitrary functions u sub k of t. So now, assuming that we have already solved the homogeneous problem, how do we solve the non-homogeneous ordinary differential equation? So let's look at the equation, non-homogeneous, that the derivative of y with respect to t equals matrix A times y plus g of t. Here, y is a column vector, A is an n by n matrix, G is a column vector. So substituting u1 f1 plus all the way through u sub n of t, f sub n of t for the y, this side becomes this stuff right here, and then the other side is going to be a times y, which is all of this, then plus g of t. So we look at this and see what we can do. First of all, let's look at the derivative with respect to t of this stuff. We need to take the derivative with respect to t of this product of functions of t plus this product of functions of t, and so on. So we'll have to use the chain rule. We'll have to use the product rule to do that. So the derivative of this first term is u1 prime f1 plus u2 prime f2 plus all the way through u sub n prime f sub n. That's half of the things that you get from the product rule. And then plus u1 f1 prime plus u2 f2 prime plus u sub n f sub n prime. So looking at this, the derivative of this first product is this term plus this term over here. And now that's supposed to equal a times this stuff, which is just what we have here, plus g of t. But now we look at this, and let's remember that result that we had earlier. The sum of the u sub k f prime of k's, sub k's, is equal to a times the sum of u sub k times f sub k. So right here, we have the sum of the u times f prime terms, and that's this one. Over here, we have a times the sum of the u sub k f sub k terms, and that's here. So this stuff here equals this stuff here. There's an equal sign here, remember. This is an equation. Okay, so this stuff in blue equals this stuff in blue. Subtract it from both sides of the equation, and we're left with this stuff right here equaling g of t. So here's what's happening. If we look at this, u1 f1 prime plus u2 f2 prime plus u sub n f sub n prime of t, that equals a times u sub 1 f times f sub 1 plus u sub 2 f sub 2 plus all the way through u sub n f sub n. This stuff in blue up here is equal to this stuff down here in blue. So they're equal quantities. Let's subtract them from both sides of this equation. The only thing that's left on the left-hand side then is this stuff up here that's in black, and we have that written right here. And on the right-hand side of this equal sign, the only thing we have left is g of t. So we subtracted equal quantities from both sides of this equation, and when we look at this equation, the functions, these vector functions, f sub 1, f sub 2 through f sub n, are known because they have to do with the solution to the homogeneous system, and g of t is known because that's the term that made our new problem a non-homogeneous system. So we know what the f's and the g's are. We want to solve these for the u sub k primes. So we have a vector equation here. The derivative of the scalar function u sub 1 of t times f sub 1 of t, this is a vector valued function here, f, plus a scalar times f2 plus all the way through u sub n prime of t, which is a scalar function, times f sub n of t, which is a vector, a column vector. This whole thing is just a column vector. G of t on the other side is a column vector too. So we want to solve these for the unknown functions, u sub 1 prime, u sub 2 prime, through u sub n prime. To do that, we'll use a little bit of linear algebra. We can rewrite this equation as the n by n matrix whose columns are f1, f2 through f sub n, times the column vector whose components are u sub 1 prime, u sub 2 prime through u sub n prime, equals g, which is the column vector g sub 1, g sub 2 through g sub n. So if we think of this first, matrix as capital F, we think of this column vector as being u prime, and this one being g. We can rewrite this as f times u prime equals g. And remember, we're trying to find the u primes. We can do that if f here is invertible, and it is. So here's what we have to do to find u sub 1 of t, u sub 2 of t, through u sub n of t. We already know that f times u prime equals g. Let's look at this matrix F for a minute. The columns of this matrix, f1 of t, f sub 2 of t, through f sub n of t, they form a set of linearly independent functions. They were coming from solutions to the homogeneous system of differential equations. So the n by n matrix capital F that we see up here is invertible. So just multiply this equation up here, left and right sides of this equation, multiply on the left by F inverse. F inverse Fu prime is just U prime. F inverse times G is just F inverse times G. So what we get is U prime of T is F of T inverse times G of T. So this column vector equals this square matrix times this column vector. To find U of T, whose components are these functions up here, we just integrate this. U of T is going to be the integral of U prime of T. So U of T is the integral of this stuff over here. The integral of f of t inverse times g of t dt. So with this knowledge in hand, we can write down the general solution to this system of non-homogeneous linear equations. The derivative of y with respect to t equals a matrix A times y plus g of t. We just found that u of t is given by this integral. So once we have this integral, assuming that we can do the integration, once we have u of t, we can plug those back into the formula for the general solution to this non-homogeneous problem up here. So y of t will equal u sub 1 of t times f sub 1 of t plus u sub 2 of t times f sub 2 of t plus u sub n of t times f sub n of t. So let's consider the following problem. Solve the derivative of x1 with respect to t equals 5 halves x sub 1 minus 1 half x sub 2 plus e to the t. The derivative of x sub 2 with respect to t equals 1 half x sub 1 plus 3 halves x sub 2 plus e to the 2t. We can write this system of differential equations in vector and matrix form as the derivative with respect to t of the vector x sub 1 of t, x sub 2 of t equals this matrix, the coefficient matrix from this part right here, 5 halves minus a half, 1 half, 3 halves, times x sub 1, x sub 2, plus e to the t, e to the 2t. So here we have a system of linear differential equations, non-homogeneous since we have this term here, written in this form. The derivative with respect to t of a vector valued function x is a times x plus g of t. So first we solve the corresponding homogeneous problem. The derivative with respect to t of x equals this matrix, call it A, times this vector, column vector x. So let's find the eigenvalues and eigenvectors of this matrix, which we'll call A. The characteristic equation is the determinant of A minus lambda I identity equals 0. And in this case, when you compute this with this matrix A, you find out that the characteristic equation is lambda minus 2 quantity squared equals 0. And so there's a double root to this characteristic equation. The only eigenvalue you get is lambda equals 2. In SageMath, we can do this calculation the following way. First, we define A to be this matrix, which we have right here, and we show it. So here it is. Let's let I be the matrix where the first row is 1, 0, the second row is 0, 1, and let's show I, and it's this 2 by 2 identity matrix. And then let's look at the determinant of A minus x times I and write it in factored form. I used an x here instead of a lambda because lambda means something special in SageMath. And so when we factor that polynomial, we get x minus 2 squared, and basically that's what we have here. The determinant of A minus lambda I equals 0, and that simplifies to lambda minus 2 squared equals 0, which gives us that eigenvalue. So we only have one eigenvalue, lambda equals 2. It is possible that we could have two linearly independent eigenvectors, both with eigenvalue 2. But let's see what happens in this case. So we basically want to solve A times, let's say the eigenvector equals 2 times that eigenvector. And we can write that as A minus 2I times that eigenvector equals the 0 vector. A minus 2I times this equals 0 as an augmented matrix is shown here. This part right here is A minus 2I, and we augmented it with a column of zeros. When you do the arithmetic here, pretty simple, we get this augmented matrix. If we take the reduced row echelon form of this matrix, we get this matrix, 1 minus 1, 0, 0, 0, 0. At the bottom, we just have a row of zeros. If we look at this, V1 is the leading variable, and V2 is the free variable. So let's let that free variable V sub 2 equal S and solve this equation for V sub 1. So we'd have V sub 1 minus S minus 1 times S equals 0. So that tells us that V sub 1 is also S. Our eigenvector V, V sub 1, V sub 2 are the components, is the vector S, S, which if we factor an S out of that, we can get S times 1, 1. So one eigenvector is 1, 1. And we only basically got one solution to A V equals 2 times V. One, let's say, linearly independent solution. We cannot find two linearly independent solutions to this equation. There's only one. So this is an eigenvector. So then the next question is, we need a second vector. We need a generalized eigenvector for lambda equals 2. So what we need to do then is to solve A minus 2I squared times that generalized eigenvector W equals 0. Well, A minus 2I squared just turns out to be the 0 matrix. So what we have here is 0 times W equals the 0 vector. Any vector W would satisfy that equation. So we can pick anything under the sun, any two-element vector under the sun, as long as it's not a multiple of 1, 1, because we're looking for two vectors that are linearly independent. So I will pick W equal to the vector 1, 0. You could have picked almost anything. You could have picked 0, 1, or you could have picked 1, minus 1 for the two components. You could not pick, for instance, 2, 2, because that would be a multiple of this eigenvector we already found. Anything except a multiple of this eigenvector, and also not the 0 vector, we could let be our value of W. So we have found two generalized eigenvectors. The first one was 1, 1. It's actually an eigenvector, but it's also a generalized eigenvector. Any eigenvector is a generalized eigenvector. The second one we picked, our vector W, 1, 0, is also a generalized eigenvector for lambda equals 2. So we have one solution up here, and here's a second solution down here to that eigenvector equation. So at this stage, we can write down the solution to the homogeneous system of differential equations given in matrix and vector form as this. It's going to be x1, x2 equals an arbitrary constant, e to the 2t times that eigenvector that we got up here. And then we'll have another arbitrary constant, c2, times e to the 2t times that second generalized eigenvector, 1, 0, plus t e to the 2t times a minus 2i, a minus 2i applied to that generalized eigenvector 1, 0. We don't need more terms here because what we saw was that w1, w2, 1, 0 was a generalized eigenvector since a minus lambda I quantity squared equals 0, so we only have to go out to this extra term. So due to the fact that this was a generalized eigenvector where the exponent m, let's say, was 2, that gives us 2 terms here. Now, it's easy to calculate a minus 2i. It's this thing here. And so we get this solution to our homogeneous problem. And then if we look at this a little bit further, this term we can write down this way. C2 times this, well, it's still here, right here, okay? And then if you multiply this matrix times this column vector 1, 0, you get this column vector 1 half, 1 half, okay? And so this solution to our homogeneous problem is in the form an arbitrary constant c1 times a vector function f1 plus an arbitrary constant c2 times a vector function f sub 2, where f sub 1 and f sub 2 are linearly independent. F sub 1 is just this thing right here, e to the 2t times 1, 1. F sub 2 of t is this stuff inside the braces, e to the 2t times this vector plus t e to the 2t times this vector. So now, with this solution to the homogeneous problem, we are prepared to find the solution to the non-homogeneous problem. Before we tackle the non-homogeneous problem, let's check to make sure that our solution to the homogeneous problem is correct. The derivative of x with respect to t equals a times x. So here is the x that we just found. I use a's here instead of c's for some reason. Basically, a sub 1, x equals a sub 1 times e to the 2t times the matrix, it's a column vector, basically 1, 1, plus a sub 2 times the following quantity, e to the 2 times t times the matrix 1, 0, plus t e to the 2t times the matrix 1 half, 1 half, the column vector 1 half, 1 half. And let's show the value of this function x at the value t. There's a slight quirk in SageMath, and I'm not quite sure why this works, but I did find somebody that did this with vector valued functions. If I want to show x of t, where I'm multiplying functions of t times matrices and so forth like this, if you want to show that vector valued function, this sort of expression works. And this is what we get. So this is the x that appears here. So let's differentiate x of t with respect to t, and we'll show what the result is. When we execute this command, we get this matrix here, and that is the left-hand side of this equation. Now let's compute the right-hand side of the equation and see if these two quantities are equal. So let's let A be the matrix whose first row is 5/2 minus 1/2. The second row is 1/2, 3/2. And then we'll calculate a times x, which is what we have here. And I'm going to store it in x2. And then I'm going to see what x sub 2 is. Show x sub 2 at t equals t. And when we do that, we get this stuff right here. And if you look at these two a little bit carefully, you'll notice that they are equal. For instance, if we look at this for a minute, here we have 1/2 times 2 times te to the 2t times a2. And so this stuff right here times this just simplifies to a sub 2 te to the 2t. And if you look at what we have over here, here we have minus 1/4 a sub 2 te to the 2t. And if we look over here, we also have 5/4 a sub 2 times te to the 2t. Okay? And 5/4 minus 1/4 is 1. And so this plus this product of these things here add up to 1 times te to the 2t, which is exactly what we had here. 1/2 times 2 is 1, and then te to the 2t. We could also check similarly to see what kind of terms we have involving a2, just e to the 2t, without a factor of t like we had here, and also the a1 a1 e to the 2t terms that we have here. The a1, I guess, is pretty easy. Here it is in this expression, and here it is in this expression down here. If you just do a little bit of simple algebra, you can easily see that this expression is equal to this expression, and this second expression in the second row is equal to this expression down here. So this column vector actually does equal this column vector. So now we're ready to solve the non-homogeneous problem by using variation of parameters. So here we have the non-homogeneous problem. The derivative with respect to t of the vector valued function x is equal to this matrix A times x plus this term that makes it non-homogeneous, e to the t, e to the 2t, and this term before we called g of t. So we've already found the solution to the homogeneous system of equations, just the derivative of x equals a times x without this extra term, and that solution was this stuff right here. Which we thought of as being c1 times f1 of t plus c2 times f sub 2 of t. So now we start variation of parameters. Let's let u sub 1 of t and u sub 2 of t be functions of t, which we will determine what they are. And we'll let x of t be the following: u sub 1 of t times this stuff plus u sub 2 of t times this stuff. So basically we just replaced the c1 and c2, which were arbitrary constants, with functions that at this point are unknown to us, whose values or expressions are unknown, u1 of t and u2 of t. We replaced the arbitrary constants with two functions of t, and now we want to figure out what functions u1 and u sub 2, what do they have to be for this stuff to be a solution to the non-homogeneous problem that we have up here. So our goal is to find u sub 1 and u sub 2 so that it satisfies this non-homogeneous ordinary differential equation. So when we look at what we have here, the f1 of t is this stuff right here, so that this first term is just u sub 1 times f sub 1. We want this stuff right here to be u sub 2 times f sub 2, as we mentioned before over here, I guess. And so f sub 2 has to be this stuff right here. And where did this stuff come from? E to the 2t times 1, 0 is 1 e to the 2t, 0, this vector here. If I multiply this column vector by t e to the 2t, we can write it this way. Okay? And so now we're ready to form our matrix F. The first column of F here is just F1, this column vector. And the second column of the matrix capital F, F is a 2 by 2 matrix, the second column is just F sub 2, which is this stuff. So we'll just add these two column vectors together, and we get this column vector right here, whose first component is, let's see, e to the 2t plus 1/2 t e to the 2t. The second component here is 0 plus 1/2 t e to the 2t, which gives us 1/2 t e to the 2t. So this matrix, capital F, this 2 by 2 matrix, just had F1 and F sub 2 as its columns. We're going to have to use F inverse in our calculation of u prime. So let's find the inverse of that matrix F. Let's do it by using SageMath. We could do this by writing an augmented matrix. We could write F augmented by a 2 by 2 identity matrix and then get it in reduced row echelon form. So this could actually be done by hand, but it's a little bit messy, so let's do it this way. So let's let F be the matrix whose first row, which we see here, is e to the 2t, which is right here, comma, e to the 2t plus 1/2 t e to the 2t, which is what we see here, comma, another bracket. And here's the stuff for the second row. E to the 2t is here. 1/2 t e to the 2t is right here. And then show F produces this output from this cell, which has basically, I guess, two commands in it. Assigning a value to F and then showing what it is, displaying it. Let's let FINV be our name for F inverse. And so what we'll do is we'll take the matrix F, which is up here at t equals t, and raise it to the -1 power. And so that will be FINV, the inverse of F, and then display F inverse. Well, here it is. The first entry in the first row is this stuff. The second entry in the first row is this stuff. The second row, first entry is this, and the second entry is this. This is the inverse of F. There's nothing more to say about it except that it looks kind of complicated. And also, we could have simplified this somewhat. We notice that here we have a couple exponentials in this factor in the first term, and it's multiplied by another exponential. So we could have used the distributive law to simplify this. E to the -4t times e to the 2t, e to the -4t times e to the 2t here. And similarly, we could have done some algebraic simplification here. If you want to do that in SageMath, what we could have had here in the show command is F inverse, parentheses, t equals t, and then dot, and then after the dot or period, simplify, underline, full. Simplify, full. And it would have done a little bit more algebra for us. So now that we have calculated F inverse, we can calculate the derivative of u, which is a column vector. It was F inverse times g, where g was that non-homogeneous term in our differential equation. G was e to the t, e to the 2t. So we need to compute F inverse of times this column vector. So let's see what happens here. I repeated some of the stuff we saw earlier. First we define the matrix F, then we compute F inverse, and here it is. And then I want to compute the derivative of u with respect to t, u being a column vector with components u1, u2. So u prime, this thing right here, is just F inverse of t times this matrix that we have right here. The first row is just e to the t, the second row is e to the 2t, as we see up here. And after we multiply this out, let's show what u prime of t is. And in this case, I will simplify it. So simplify full, okay? And parentheses after the full, and we also have parentheses here matching with the one here for that show command. And so u prime is this thing right here. Still, it could be multiplied out, I guess, a little bit more, but in any case, this is pretty simple, and we'll go from here. We'll use this. So far we have calculated u prime by multiplying F inverse times the vector function g. And now what we want to do is to get u. And we get that by integrating u prime with respect to t. So let's see how we can get this. Once again, there's a little bit of repetition in the commands here. First we calculate u prime as we saw before, and we show what it is, and here it is. Okay, I'm going to introduce a couple variables which are going to represent the arbitrary constants involved in integration. C underline 1 and C underline 2 are going to be variables, and here they are. When I show these variables in an expression, they'll look like the 1 and 2 are subscripts, which is what I'm after. Okay, now to find u, we have to integrate u prime. And I'm going to do it in two parts. I'm going to find u1 by integrating u1 prime, and I'm going to find u2 by integrating u2 prime. And so here's what we'll do. u1 is going to be the integral of, and then the stuff that we see here is just the first component of u1 prime, which we have up here. Okay, and then after integrating that, the integrate starts after this left parentheses and ends with this right parentheses here. I'm going to add an arbitrary constant c sub 1 to it because SageMath doesn't put that in for us. And then I'll show what u sub 1 is. Okay, so after we execute this statement along with the show u sub 1, what we get is u sub 1 is this stuff right here. 1/4 t squared plus 1/2 t plus 1 times this exponential plus c sub 1 plus t. Okay, then we'll do the same thing to calculate, a similar thing to calculate u sub 2 here. We'll integrate u sub 2 prime, which is just this stuff down here, the second component of u prime. So we'll integrate u sub 2 prime with respect to t, and then add an arbitrary constant c sub 2 to that, and then next command show u sub 2. And it turns out to be c sub 2 minus t minus e to the minus t. So at this stage, we have found u sub 1 and u sub 2 right here for u sub 1 and right down here for u sub 2. So we're almost finished solving that non-homogeneous system of differential equations. We're now ready to compute the general solution. Let's remember that x of t, the solution to the non-homogeneous problem, is going to be u sub 1 of t times f sub 1 of t plus u sub 2 of t, f sub 2 of t, which in our case is u sub 1 of t, and then f sub 1 of t was e to the 2t 1 1, and then we had u sub 2 of t times f sub 2 of t, which is this stuff right here. Probably I should have put in parentheses t here and parentheses t here to remind us those are functions of t. And let's use SageMath to do the computation of this thing. So we'll let x equal u sub 1 evaluated at t equals t times f sub 1, which is this stuff right here, plus, and then u sub 2 evaluated at t equals t times f sub 2, which is that stuff right there, which is written right here. For instance, matrix 1/2 1/2 is this column vector right here. And then we're going to show x of t, and we're going to simplify it fully. Simplify, underline, full. And so what we get is that x sub 1 is equal to this stuff. 1/4 the quantity of 2c sub 2t minus t squared plus 4c sub 1 plus 4c sub 2, all that times e to the 2t minus 1/2 e to the t. Similarly, u sub 2 of t is this stuff right here. So we have calculated the solution, the general solution to that non-homogeneous problem. We did not have an initial value problem, so we don't have any way to find C1 and C sub 2 in this particular case. But if we did have initial conditions, we could solve for C sub 1 and C sub 2. But at this stage, we have displayed a purported and alleged solution to our problem. It would be nice to check to see if this function, this vector valued function, x of t, actually solves that non-homogeneous differential equation. So let's see what we can do with that. So we want to check to see if that function x of t, that vector valued function, satisfies this non-homogeneous system of differential equations. So what we'll do in SageMath is to calculate the left-hand side, calculate this right-hand side, and then inspect those two to see if they are equal or not. Okay, so to reiterate, we'll compute the left-hand side, which is the derivative with respect to t of x of t, and the right-hand side, which is this stuff, and then use our eyeballs to compare them. So let's look at this first command. Show, and basically the derivative of x of t with respect to t, and simplify it full. We're calculating this left-hand side, and when we do that, we get this vector. It's a column vector. The top entry in the column is this stuff. It's kind of long. The second component of this column vector is all of this stuff. It's just basically 2 rows, 1 column. So that's the left-hand side. For the right-hand side, let's look at this command. X sub 2 is a times x, and a, remember, was already inputted as this matrix, plus the matrix e to the t, e to the 2t. So a times x plus this vector right here. And then we want to see what that is. So show x sub 2 of t, basically, and once again simplify it fully. Simplify, underline, full, with a dot here. So we're taking whatever this is, an algebraic expression, and simplifying it, and that's what we're showing. And when we do, we get this stuff. This is actually easier than the last comparison we did visually, because if you look at these two column vectors, they're written identically in this case. So when we computed this left-hand quantity, we got this. And when we computed this right-hand side, we got this. And clearly they are equal. So the function x that we found actually does satisfy this equation. One thing that I should point out here, I guess, is that I didn't actually use x sub 2 in SageMath to be the second component of x. This is the first time it appeared, and I just happened to use it to be the second component of this side. I let x sub 2 be the vector valued function computed from this side. And so this stuff up here was this entire thing here. What I computed down in the second one was this entire thing here, and they are equal. So what did we do in solving the non-homogeneous problem? First, we found the solution to the homogeneous problem. X prime equals the matrix A times x of t, and it looked like this with some arbitrary constants c1, c2 through c sub n, and some functions, vector valued functions f1, f2 through f sub n. Secondly, we looked for a general solution to the non-homogeneous problem. X prime equals ax of t plus g of t, and it had this form: u sub 1 of t times f1 plus u sub 2 of t times f sub 2 plus all the way through u sub n of t times f sub n. To find these u functions, we solved this equation: u1 prime f1 plus u2 prime f2 plus all the way through un prime fn equals g of t. Solve those for the u prime functions that you see up here. We integrated that to find the u of t functions that were up here. And once we knew what the u of t's were, u sub 1 of t, u sub 2 of t, through u sub n of t, we were then able to use these to write the general solution of the non-homogeneous problem using this formula for it right here. I hope you enjoyed this video. Please stop by again. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.